In episode 1, we set up the central idea: linear algebra is geometry. In this episode, we slow down and look at the objects that make that geometry measurable: vectors, basis, and coordinates. A vector is not just two numbers. A basis is not just a pair of arrows. Coordinates are not the object itself. Coordinates are readings taken with a chosen set of rulers. Once that distinction is clear, many later formulas stop feeling like symbolic manipulation. They become visible statements about space. Start with the vector. Geometrically, a vector can be a displacement from one point to another, or a free arrow with length and direction. If you slide the arrow without rotating it or stretching it, it is still the same vector. The coordinates only appear after we choose axes. On the standard grid, an arrow might be 3 units to the right and 2 units up. In another set of axes, the same arrow can have a different pair of numbers. The object is the arrow. The numbers are how a coordinate system describes that arrow. Vector addition is movement composition. To add 2 vectors, first move along the first arrow, then place the second arrow at the tip and move along it. The resulting arrow goes from the original start point to the final end point. The parallelogram picture says the same thing in a more symmetric way. This is why coordinate addition works. The x readings add because horizontal movement accumulates. The y readings add because vertical movement accumulates. The calculation is bookkeeping for a visible geometric action. Scalar multiplication changes how far we travel along a direction. If the scalar is greater than 1, the vector stretches along the same line. If it is between 0 and 1, the vector shrinks. A negative scalar flips the arrow to the opposite direction, then scales it. Multiplication by 0 collapses the vector to the origin. The important geometric point is that scalar multiplication does not create a new direction. It keeps the vector on the same one-dimensional line. So when you see k times v, picture a slider moving back and forth on a line through v. A linear combination is the basic move that keeps returning throughout linear algebra. You choose a few directions, then choose coefficients that say how far to walk along each one. For example, c1 times u plus c2 times w means walk some amount in the u direction and some amount in the w direction, then combine the movements. Positive coefficients walk with the arrow. Negative coefficients walk against it. This simple idea is behind matrix columns, linear systems, projections, and decompositions. The question is always geometric. With these available directions, what targets can we reach? The span of a set of vectors is the collection of everything you can build from their linear combinations. One non-zero vector spans a line because all scalar multiples stay on that line. 2 non-parallel vectors in a plane can span the whole plane because you can move in 2 independent directions. In 3 dimensions, 2 independent vectors span a plane through the origin, and 3 independent vectors can span all of space. A subspace is a reachable set that stays closed under vector addition and scalar multiplication. If you add 2 reachable vectors, you remain reachable. If you scale a reachable vector, you remain reachable. Linear independence tells us whether a direction is genuinely new. If one vector can already be made from the others, it is redundant. It does not expand the set of places we can reach. In the plane, 2 arrows pointing along the same line are dependent, because they still only span that line. 2 non-parallel arrows are independent, because neither one can be built from the other. A basis is a set of vectors that is both independent and large enough to span the space. For the plane, a basis needs exactly two independent directions. For ordinary three-dimensional space, it needs three. Coordinates are not the vector. They are the coefficients used to build the vector from a chosen basis. In the standard basis, the vector v might equal x1 times e1 plus x2 times e2. That means walk x1 units along the first basis direction, then x2 units along the second basis direction. The coordinate pair is a compact record of that decomposition. This is why the question, what are the coordinates of v, is incomplete unless we know the basis. Coordinates always mean coordinates relative to some measuring system. Change of basis is a translation between coordinate languages. The geometric vector stays fixed. What changes is the coordinate grid used to describe it. In the standard basis, the vector may have one pair of readings. In a tilted basis, the same vector gets a different pair. Nothing physical moved in space. Only the measuring rulers changed. This distinction is crucial later because matrices can represent two related ideas. They can describe an active transformation of space, or they can describe a passive change in how we write coordinates. Here is the core picture to keep. A vector is a geometric object, a direction and length, often interpreted as a displacement. A linear combination builds new vectors by scaling and adding available directions. The span is the full reachable set produced by those combinations. A basis is a non-redundant set of directions that can describe the whole space. Coordinates are the coefficients of a vector in a chosen basis. So whenever you see a coordinate vector, ask, which basis is this written in? In the next episode, we use this foundation to understand matrices as transformations of the entire space.